Let us consider a setup with a uniform electric field and a plane surface perpendicular to the electric field lines. Now, flux is essentially the number of electric field lines that pass through the surface. Technically, the number of field lines is infinite, but we do consider flux to be a non-infinite quantity. So we would define the flux as the product of the electric field and the surface area. Now, electric field is obviously a vector quantity, but what about flux and surface area? Now, surface area can be represented as a vector, and to understand that, let's look at this figure over here. Here we have a quadrilateral, and the two adjacent sides are denoted by vectors A and B. Now, when you get the cross product of the two vectors, that gives you a third resultant vector, which we're going to call S, which is the area vector. Now the direction of this is perpendicular to the plane of the surface, and the magnitude is equal to the area of the quadrilateral. So let us place a vector sign over the S. So now we know that flux is a result of the electric field and the surface area. But do we use a dot product here or a cross product? How do these two vectors interact? Now I'll give you a spoiler, it's a dot product, but why is that? Now let's consider the surface area vector, of course, which I haven't drawn yet. This is the surface area vector, and these are the electric field vectors, right? So now what is the angle between the electric field and the surface area vector? That is 0. Let's talk in terms of degrees. So that is 0, and the flux is maximum when the angle is 0, which means that the flux would be minimum if the angle were 90 degrees. In this case, in an alternate surface where the surface is parallel to the electric field lines, let's call this S prime, then there would be no field lines passing through it whatsoever, and the angle between the electric field and the surface vector would be 90 degrees. What this means is that the flux also depends on the angle between the electric field vector and the surface area vector. So F is equal to ES. We'll consider the magnitude of the field and the surface area and not the direction, so we're just going to write them down as scalars. Now we have to multiply this by the cosine of theta. Right? Because when theta is equal to 0 degrees, cos theta is 1. And when theta is 90 degrees, cos theta is 0, which is the flux when, as I showed before, which is the flux when the electric field lines and the surface area vector are mutually perpendicular. So this is basically the definition of the dot product. The first vector multiplied by the second vector multiplied by the cosine of the angle between them, which is why we use a dot here. So now we can finally have the definition, which is phi equals E dot S. That is the definition of electric flux. Now let's talk about Gauss's law. Gauss's law deals with the electric flux through a sphere, or like the electric flux through a body which encloses a charge. Let's specifically talk about a sphere here. So now let's say the sphere contains a charge q within itself. Right? So now we would like to find the electric field exerted by, or the electric field produced by the charge q at the edges of the sphere. Keep in mind that the sphere is hollow, it does not have anything inside it except for the charge. And the sphere has a radius of r. So now the electric field is defined as k q by r squared, where k is Coulomb's constant. And now this k could be written as 1 by 4 pi epsilon naught. And that could be multiplied by q by r squared. Sorry. Yes. So now we have the value of E in this case. Let's also find the value of S. Now the surface area of this sphere is just 4 pi r squared. That's the surface area of any sphere. And now in order to find the flux through the walls of the sphere, we multiply E and A. The flux is equal to E. I'm sorry, not E and A, E and S. So this is just 4 pi epsilon naught into q by r squared. And now we multiply this by S, which is 4 pi r squared. Now let's look at the terms which can cancel out. The 4's cancel out, the pi's cancel out, and the r squared cancels out, sorry. So now this leaves us with q by epsilon naught. So here we have the final value of flux, which is q by epsilon naught. This applies when a charge is enclosed by any hollow object. It doesn't necessarily have to be a sphere. It could be a cube or any polyhedron whatsoever. Now the reason that this applies to any shape and not just a sphere is because of a very simple reason. Think about all the electric field lines that emanate from this charge in all directions, right? So now ultimately they will reach the surface of the sphere, and all of them do reach the surface. So this is essentially all of the field lines that the charge produces. So it doesn't matter how big the sphere is, the number of field lines that will pass through the sphere will be the same. And the number of field lines that pass through the surface depends on the charge enclosed by the sphere, or whatever surface we take. Thank you.